Good day. Spectroscopy Module 3. Today we are learning about instrumentation of UV and visible spectroscopy. Before describing the parts of instruments, there are different instruments like colorimeters, spectrophotometers. Let us study the different components of these instruments. Source of light, filters and monochromators, samples as detectors. Source of light used in visible region are tungsten lamp and carbon arc lamp. Source of light used in UV region are hydrogen lamp, deuterium lamp, xenon lamp, mercury arc lamp. Filters and monochromators. Filters are absorption and interference filters. Monochromators, prisms and gratings. Sample cells. Detectors used are photovoltaic cell, phototubes, photomultiplier tubes. You can see the block diagram of instrumentation. Consists of light source, monochromator, sample cell, detector. Let us study one by one. Source of light. The source of light used in visible spectrum ranges from 400 to 800 nanometers. Hence, any lamp source which gives adequate intensity of radiation over the entire wavelength region can be used. Requirements of a source of light. Source of light used in visible region should provide continuous radiation over the entire wavelength region, that is from 400 to 800 nanometers. Also, it should provide adequate intensity of radiation. And also, source of light used in visible region should be stable and free from fluctuations. Source of light used in visible region are tungsten lamp, carbon arc lamp. Tungsten lamp. It is most common source of visible radiation. The lamp consists of tungsten filament in a vacuum bulb similar to the household lamp. You can see the diagram here. It consists of a piece of tungsten wire which is heated in a controlled atmosphere. Drawback here is tungsten lamp emits major portion of its radiant energy in the near IR region of the spectrum, and only 15% of the radiant energy falls within the visible region. It can be overcome by placing heat absorbing filter between the lamp and sample. Carbon arc lamp. For a source of very high intensity, carbon arc lamp can be used. It also provides an entire range of visible spectrum. UV region. In the UV region, the source of light used are hydrogen discharge lamp, deuterium lamp, xenon discharge lamp, mercury arc lamp. UV spectrum ranges from 200 to 400 nanometers. Hence, any lamp source which gives adequate intensity of radiation over the entire wavelength region can be used. Hydrogen discharge lamp. It is most stable, robust and widely used. It gives radiation from 120 to 350 nanometers. The lamp consists of hydrogen under high pressure. The hydrogen molecules are excited electrically and emit UV radiation. You can see the diagram of hydrogen discharge lamp. Deuterium lamp. It is similar to hydrogen discharge lamp but filled with deuterium in place of hydrogen. It offers 3 to 5 times more intensity than other type of sources. This is the most widely used in UV spectroscopy, but it is expensive. You can see the diagram here. Xenon discharge lamp. In this lamp, xenon at 10 to 30 atmospheric pressure is filled in and has 2 tungsten electrodes. The intensity is greater than hydrogen discharge lamp. This is the xenon discharge lamp. Mercury arc lamp. This contains mercury vapor and offers bands which are sharp, and the spectrum here is not continuous, so it is not widely used. These are the sources in UV region. Next, coming to the filters and monochromators used in UV visible spectroscopy. The source of light gives radiations from 400 to 800 nanometers. This source of light emits radiations. These radiations are called as polychromatic radiations. In photometry or colorimetry or spectrophotometer, we require only monochromatic radiations. Hence, single wavelength is used for the absorbance of sample. Hence, a filter or monochromator are used which converts polychromatic light into monochromatic light. Here two kinds of filters are used, absorption filters, interference filters. Monochromators are of two kinds, prism type, grating type. Filters. Absorption filters. These filters are made up of glass coated with pigments or they are made up of dyed gelatin. The function of absorbance filters are they absorb the unwanted radiation and transmits the rest of the radiation which is required for colorimetry. These filters can be selected according to the procedure given below. So this comes under construction and working also. First, draw a filter wheel. Write the colors VIBGYOR in clockwise or anti-clockwise manner omitting indigo. If the color of the solution is red, we have to use green filter. And if the color of the solution is green, we have to use red filter. The color of the filter is opposite to the color of the solution. This is complementary in nature. Similarly, we can select the required filter in a calorimeter based upon the color of the solution. Merits are simple in construction, cheaper, selection of the filter is very easy. The demerits are less accurate because the band pass is more, that is plus or minus 30 nanometers. What is band pass? Band pass means if you have to measure at 500 nanometers of a sample. What will happen here? The radiation from the filters falls at a range of 470 nanometers to 530 nanometers. This is called band pass. And we can define it as band pass is the difference in wavelength between the points where the transmittance is one half the maximum. Intensity of radiation becomes less due to absorption by filters. Next one, interference filter or Fabry-Perot filter. Here the construction and working of these filters are, you can see the diagram here. It consists of a dielectric spacer arm made up of calcium fluoride, magnesium fluoride or silicon dioxide between two parallel reflecting silver films. The thickness of the dielectric spacer films can be 1/2 wavelength or 2 by lambda or 3 2 by lambda. The mechanism is that the radiation reflected by the second film and incoming radiation undergoes a constructive interference to give a monochromatic radiation. You can see in the diagram how the polychromatic radiation is changing to monochromatic radiation. So here the polychromatic radiation can be converted into monochromatic when the radiation reflected by the second, this is the second film, and the incoming radiation undergoes, this is the first film. From this the radiation enters. So here the reflection by the second film and the incoming radiation undergoes a constructive interference to give a monochromatic radiation. This can be governed by the following equation. Lambda is equal to 2 nu b by m, where lambda is equal to wavelength of light obtained, nu dielectric constant of layer material, b is the layer thickness, m is the order number. For Fabry-Perot filters, band pass is 10 to 50 nanometers and maximum transmission is 40%. Merits are, it is inexpensive, lower band pass when compared to absorption filters and hence more accurate. Use of additional filter cut off undesired wavelengths. But the demerits are peak transmission is low. The band pass is only 10 to 50 nanometers and hence higher resolution obtained with monochromators or gratings. Next, coming to the monochromators. Monochromators are better and more efficient than filters in converting a polychromatic light or heterochromatic light into monochromatic light. You can see here the monochromator consists of following units. First one is entrance slit. This is the entrance slit. Entrance slit is used to get narrow source. Next one is collimator. Collimator is to render light parallel. Next, it consists of grating or prism. These grating or prism used to disperse radiation. Again, collimator. It is used to reform the images of entrance slit. Exit slit to fall on the sample cell. So, these are the components of monochromators. Monochromators consist of entrance slit, collimator, grating or prism, collimator, exit slit. Let us see the different types of monochromatous. Monochromatous are of two types. Prism type. Prism type are of two types. Dispersive type and lithotype. Grating type. Again two types of grating type. Diffraction grating, transmission grating. Prisms. The function of prisms are to disperse light radiation into individual colors or wavelengths. These prisms are found in inexpensive instruments. The bandpass is lower than that of filters and hence it has better resolution. The resolution depends upon the size and refractive index of the prism. The material of the prism is normally glass in visible region. There are two types of prisms are available. Refractive type. You can see the diagram, the refractive type of prism here. So here in the refractive type of prism, the source of light through the entrance slit falls on the collimator. The parallel radiations from collimator are dispersed into different colors or wavelengths, and by using another collimator, the images of entrance slit are reformed. The required radiation on exit slit can be selected by rotating the prism or by keeping the prism stationary and moving the exit slit. Next, coming to the reflective type or lithotype mounting. A total reflecting prism is a prism that reflects the light that falls normally on its faces. A reflective surface is present on one side of the prism, hence a dispersed radiation gets reflected and can be collected on the same side as source of light. You can see here the diagram. On one surface, it is coated with a reflective surface, this is, and where the incident radiation is falling on the prism, on the same side you can see the dispersed radiation also. Next, coming to the gratings. Gratings are most efficient one in converting polychromatic to monochromatic light. As a resolution of plus or minus 0.1 nanometers, these are the most commonly using in the spectrophotometers. And there are two different types of gratings, diffraction grating and transmission grating. Diffraction gratings. You can see the diagram here. Here gratings consist of rulings. The lines which are present are called, these are called rulings. So here the lines are made up of some material like glass in the visible region, quartz in the UV region or alkyl halides in IR region. Depending upon the instrument, the number of rulings per mm ranges from 20 grooves or lines per mm for IR spectrophotometer to 3600 grooves or more per mm for UV or visible spectrophotometer. You can see the diagram here. These gratings are replica made from master grating by coating the original master grating with epoxy resin and are removed after sitting. To make the surface reflective, one side of the surface is coated with alumina. The mechanism is that diffraction produces reinforcement. That means the rays which are incident upon grating gets reinforced with the reflected rays and hence the resulting radiation has a wavelength which is governed by the equation. You can see in the diagram here. So here the mechanism is diffraction produces reinforcement. When the incident rays fall on the grating, it will get energized and hence the resulting radiation that is emitted has a wavelength. It can be calculated by the equation. You can see the equation here, m lambda is equal to b sin I plus or minus sin r, where lambda is equal to wavelength of light produced, b is the grating space, sin I is the angle of incidence, sin r is the angle of reflection and m is the order number. Next, coming to the transmission grating. Transmission grating is similar to diffraction grating, but here instead of reflection, refraction takes place. Mechanism is refraction produces reinforcement. This occurs when radiation transmitted through grating reinforces with partially refracted radiation. The wavelength of radiation produced by transmission grating can be expressed by the following equation. Lambda is equal to d sin theta by m, where lambda is the wavelength of radiation produced, d is the 1 by lines per centimeters, theta is the angle of deflection or diffraction, m is the order number. Next, coming to the sample cells or cuvettes. The function of sample cell or cuvette is to hold sample solution. Here the material of sample cells used are different from region to region, and also the material of sample cell should not absorb at the wavelength being absorbed. Let us see some parameters and availability. Sample volume. Sample volume cells are available at 0.5 ml or from 5 to 10 ml. Shape of the sample cells are cylindrical or rectangular. The path length, that is internal diameter, are available 1 to 10 centimeters for longer path lengths and also 1 mm or 2 mm for shorter path lengths. Whereas material here is glass in the visible region, quartz in the UV region. Next, coming to the detectors used in UV or visible spectrophotometers. These detectors are also called as photometric detectors. The principle involved in detector is when a radiation is passed through a sample, part of it being absorbed by the sample solution and the rest is being transmitted. This transmitted radiation falls on the detector and the intensity of absorbed radiation can be determined or displayed. In these detectors, the light energy is converted to electrical signal which can be read or recorded. Requirements of ideal spectrophotometric detectors. The detector should give a quantitative response. It should have high sensitivity and low noise level. It should have a short response time. The detector should provide a signal or response quantitative to the wide spectrum of the radiation received. The most commonly used detectors in the UV or visible region are barrier layer cell or photovoltaic cell, phototubes or photoemissive cells, photomultiplier tubes. Barrier layer cell or photovoltaic cell. These cells are inexpensive and are used in inexpensive instruments like filter type colorimeters, fluorimeters and nephroturbidimeters. Principle involved in photovoltaic cell is generation of potential difference when the transmitted UV or visible radiation falls on the semiconductor layer. Construction. The detector has a thin metallic layer coated with silver or gold and acts as an electrode. It has a metal base plate which acts as another electrode. These two layers are separated by semiconductor layer of selenium. Selenium has extremely low electrical conductivity and electrons are not mobile. Working. When light radiation falls on the selenium layer, these electrons become mobile and are taken up by the transparent metal layer. This creates a potential difference between the two electrodes, causes the flow of current when the resistance in the external circuit is small. This flow of current causes deflection of the galvanometer needle, which depends on the wavelength and intensity of radiation. The disadvantage with the photovoltaic cell is the amplification of signal is not possible. Phototubes are photoemissive cells. The principle involved in photoemissive detector is emission of electrons from photocathode and subsequent capturing of electrons by the anode, resulting in the flow of current. Construction. This detector is composed of an evacuated glass tube which consists of photocathode and a wire anode or collector anode. The photocathode is coated with elements of high atomic volume like cesium, potassium or silver oxide, which can liberate electrons. Composite coatings like cesium oxide, silver oxide can also be used, which increases the sensitivity and range of wavelength of detector. Working. When light radiation falls on cathode, this causes flow of current towards anode and produces a current proportional to the intensity of light radiation falling on the detector. The signal from the detector can be amplified using a amplifier circuit. Phototubes have better sensitivity when compared to photovoltaic cells and hence these are more widely used. Photomultiplier tubes. This type of detector is most sensitive of all detectors, expensive and used in sophisticated instruments like spectrophotometers. Principle involved in photomultiplier tubes is multiplication of photoelectrons by secondary emission of electrons. Construction. In a vacuum tube, the primary photocathode tube is fixed. This is the primary cathode tube, which receives the transmitted radiation from the sample. The multiplication of electrons is achieved by using a photocathode and a series of diodes. These are the diodes. The photomultiplied tube can use up to 10 diodes. Hence, the detector can detect even very weak signals, that is 200 times weaker signals can be detected by photomultiplied tubes. The diodes are maintained at 75 to 100 volts higher than the preceding diode. Working. When the radiation from sample falls on cathode, cathode emits electrons onto the first diode. The first diode receives electrons and from the first diode, some electrons from the surface get emitted. These electrons get bombarded on the next diode surface due to higher potential. The transfer of kinetic energy from the bombarding electrons results in the emission of even more electrons than the surface of the second diode. The same procedure keeps on happening and the electrons keeps on multiplying from diode to diode. They finally hit the anode or electron collector electrode, which displays the signal into the readout device. Advantages. These produces wide spectral response, high stable. Disadvantages. Mechanically fragile, made up of glass envelope, and these are expensive. Silicon photodiode array detector. Principle involved in silicon photodiode array detector is a sensor with multiple silicon photodiodes. A silicon photodiode utilizes the internal photoelectric effect, the phenomenon whereby the electrical properties of the detector itself change when light strikes it. Working. A silicon photodiode is a semiconductor. When light coming from the sample falls on this semiconductor, the energy of the light, if it is greater than the band gap, electrons in the valence band are excited into the conduction band and holes are left in the original valence band. These electron-hole pairs are created throughout the semiconductor, but in the depletion region, the electron field causes electrons to be accelerated towards N region and holes to be accelerated towards P region. As a result, electrons accumulate in the N region and holes accumulate in the P region, and the two regions become respectively negatively and positively charged. If this is connected to a circuit, current flows. The band gap of silicon is approximately 1.12 electron volts. So current flows only for wavelengths that have an optical energy greater than this. This works out a wavelength upper limit of around 1100 nanometers. Advantages over photomultiplier tubes. When compared to photomultiplier tubes, these detectors are less expensive, high sensitive, and greater wavelength range than the photomultiplier tubes, usually from 180 nanometers to 1100 nanometers. And these detectors are more robust. Unlike photomultiplier tubes, diodes do not require a higher voltage power supply, which are expensive. These are the detectors used in UV and visible region. Next, coming to the instruments available in UV visible spectroscopy. The instruments are single beam colorimeter, double beam colorimeter, double beam spectrophotometers. In single beam colorimeter, the lamp used is tungsten lamp, and here the wavelength selectors or filters are used and detectors or barrier layer cells are used. Why it is called single beam colorimeter means here the wavelength should pass through the sample and reference separately. Next one is double beam colorimeter. In the double beam colorimeter, the light source used is tungsten lamp And here the monochromators or filters are used and the detector or phototube cells are used. And here in the double beam colorimeters, the light beam after passing through the filter or monochromator is split into sample beam and reference beam by using a beam splitter. You can see the beam splitter. And double beam spectrophotometers, these are advanced spectrophotometers, and the light source used is tungsten filament lamp in the visible region and deuterium lamp in the UV region. And for wavelength selection, gratings are used. And detector is photomultiplier detector. For more information, you can go through the link.